This is exercise 6C on factorization of polynomials on page 220 of your textbook. Last lesson we talked about how do we divide polynomials. We can divide them by using our long division algorithm, something that we're quite familiar with throughout the last few years using numeric division. So just as a revision, I'm going to do the same thing with these variables right here, just as a quick brief revision of what we've learned so far. I'm going to do that down here just so we have enough space. I've got x squared plus 7x plus 11, and then divide that by our divisor, which is x plus 2. Now the first question I have to ask myself is, what do I have to multiply this leading term by in order to get this leading term? X, exactly right. I can times it by x. I get x squared plus 2x. So what I've done is I multiplied that by x, then multiplied that by x as well. So inherently, what operation is it? Is it adding, subtracting, multiplying? Subtracting, thank you very much. So from there, x squared take away x squared is obviously 0. And then 7x take away 2x gives me 5x. Keely, is that a question? No? Okay. Same thing. How do I get this leading term to be the same as that leading term? What do I multiply by? Sophie? Jones? What do I multiply this leading term by to get to this leading term?
Are you asking me?
Yes. So I'm bringing this down, right? So I get plus 11. What do I have to multiply this by to get the same leading term as that one? 5. Easy. So I'm going to multiply by 5. Positive or negative? Positive 5. I'm going to write positive 5. I get 5x plus 10 because I'm multiplying the whole thing by 5. That is terrible handwriting. There we go. Once again, inherently my operation is a takeaway. So I end up with a final answer of 1. What is that 1? It's a remainder because I can't divide it any further, right? So my final answer I can write as, well, x, that's not an x, there we go, x squared plus 7x plus 11, that's my original equation, equals to what I divided it by, x plus 2, times by what my quotient was, so x plus 5, and then plus my remainder, which is 1. If I was to go ahead and double check this using a calculator, how would I double check this is correct? Perfect. If you just expand that in the calculator, and there is an option for that, if you expand it in your calculator, you should, oh, not cross that out, you should get that. You should get that. That's how you double check if you're correct. So, perfect. That is the way that we do polynomial division. And typically for exercise 6b, what will be done is it will give you this equation, and then it'll say divide by this equation here. So divide this by that. But what happens if you have to find that divisor itself? In other words, instead of being told what to do, what if you have to find what you have to divide by? In which case, well, you have to try and find what's divisible. Our remainder theorem, sorry, our factor theorem is looking at, well, if I find the factor and it's a perfect factor, what should my remainder be? 0. So you should be able to fit perfectly into that equation there. But let's focus on the remainder theorem first. The remainder theorem over here, and it's up here, tells me that when p of x is divided by d of x, where d of x equals to beta x plus a, if you want to just read it as b x plus a, that's fine. The remainder is given by p negative a over b. If I'm putting it in simpler terms, if I let the divisor, in this case, what's the divisor? Thank you. X plus 2 is the divisor. If I let the divisor equal to 0, I'm going to go ahead and try and make some space over here. There we go. If I let the divisor equal to 0, so x plus 2 equal to 0, what is x equal to? Well, negative 2. Now the idea is, what the remainder theorem tells us is we can find the remainder by just substituting this value in. Now it's not saying that we can immediately solve and find all the factors, whatever, but it's just saying we can just off the bat find the remainder. And if we can find the remainder and it ends up being 0, then it's a perfect factor, right? So let's go back to that step of finding the remainder. From here, we do this thing over here. What does that in brackets mean? What does that thing tell me? What do we have to do? We have to sub it in, don't we? So remember, at the start of the year, I talked about f of x. Instead of f of x, what happens if you write f of negative 2? Well, every time we see x, we substitute negative 2. So I go, well, original equation over here. I substitute, I get negative 2 squared plus 7 times negative 2 plus 11. Are we okay with that? All I've done is substituted negative 2 into that original equation. So negative 2 squared gives me what, Tom? 4. Minus 14 plus 11. Minus 14 plus, 4 minus 14 gives me what? Plus 11. 1. So we've immediately found our remainder. And it's the same one as we got down here using the long division method. So they're both fine, but the long division method actually gives you a quotient, whereas the remainder theorem doesn't give you anything besides the remainder. Does that make sense? Yeah? So we can use that to trial and error, essentially, and look for a perfect factor. So, for example, in this question it says, find the remainder when p of x equals to x cubed minus 3x squared plus 2x plus 6 is divided by the equation x minus 2. So what's the first thing I did over here? Oops. What's the first thing I did over here? Kaylin? What's the first thing I did in the circle? Yeah, I found negative 2, and that's because I let the divisor equal to 0. Okay? So from there, I'm going to do the same thing. That's what this formula tells us, by the way. When we let the divisor equal 0, we find x and sub it in. So over here, same thing. My divisor is x minus 2. So if x minus 2 equals to 0, I don't know if you guys can see that up the back. Evelyn, can you see that? Yeah. Then x equals to positive 2. I'm going to substitute that in. I'm going to write p of positive 2, which equals to 2 cubed minus 3 times 2 squared plus 2 times 2 plus 6. Are we okay with that? All I've done is I've substituted the value of 2 in, which equals to 2 cubed is 8. Thank you very much. Take away 3 times 4, which is 12, plus 4, plus 6. 8 take away 12 is a negative 4, and then plus the rest is positive 6. So our remainder is 6. Does x minus 2 go neatly into this p of x? No, why not? Good, because there's a remainder that isn't 0. And so what we can do is we can try and trial and error. In this case, I'm not going to go through that. Let's go. Actually, should I? Yeah, let's go through it. All right, so in this case, what we're going to do is we're going to do the same thing. We're going to try and find the actual divisor. So in this case, let me try and find an example. Apologies, I should have prepared this earlier. Okay, so if I have x cubed plus x squared minus 14x minus 24, what we can do is it's something similar to the cross method in the sense that we want to look for something that actually multiplies to give me 24. In other words, a factor of 24. Now, why is cross method similar to this? Well, it's because they're both methods of factorization. Cross method factorizes what kind of polynomials? Quadratics. Whereas this applies to cubic functions. And when we expand it, if I go back to this form over here, which we found, in this form, if I'm ignoring the remainder, obviously there's no remainder if it's a perfect factor. If I'm ignoring the remainder, would you agree that only these two numbers multiply to give me my last constant over here? They have to, because that's how expanding works. Similar in the same vein, how the first two terms have to multiply to give me my first one. Because we know there's all like these numbers, for example, if I go x multiplied with positive 5, and then 2 times x, we have to add it up, subtract it, whatever it is. It gets a bit confusing, but we know for sure that the first term has to multiply, has to be a factor, or multiple, of these two over here, these two terms there. So we can keep that in mind. So what's a factor of negative 24? Give me any factor. Sorry? Alright, let's try 6. So if I say x equals to oops, my apologies. If I'm saying, I'm trying to find 6, I substitute negative 6. Let's say that's P of X. So P of X equals to negative 6. Or in other words, you said that X equals to positive 6. So from there, I substitute it, I get P of negative 6. So that should have been of negative 6, my apologies. There we go. Equals to negative 6 cubed plus x, not x, sorry. Negative 6 squared minus 14 times negative 6 minus 24. Now, I personally wouldn't have started with such a large value, but it could work. Let's give it a go. What's 6 cubed? 216. Is it? I feel like double checking that. I feel like it's right. I'm just going to double check that. I feel like it would have been faster for me to do this by hand. Come on. Come on. There we go. It is 216. Well done. Thank you very much. So 216, positive or negative? Negative, good. And then plus 36 plus 60, 84 minus 24. These are absurdly large numbers. But off the bat, can you tell whether that's 0 or not? Is it going to be 0? It's not going to be 0. We have a negative 216 up the front, and then we have 36 and 84 adding. That's not going to end up being 0. So I know that doesn't equal 0, and therefore it's not a factor. What about if I had, let's say, x plus 2? Or actually, let's do that, x plus 2. If I'm looking for whether x plus 2 goes in, I let it equal to 0, x plus 2 equal to 0, and x equals to negative 2. Are we okay with that? I'm going to do the same thing. P of negative 2, which gives me, I have to go back up, there we go. So I'm substituting negative 2 for each time I see x, negative 2 cubed plus negative 2 squared, minus 14 times negative 2, minus 24. So equals to, negative 2 cubed is 8, negative 8. And then I get plus 4 plus 28 minus 24. Negative 8 plus 4 gives me negative 4, that's right. Negative 4 plus 28 minus 24 gives me 0. So what does that tell me about this right here? What is that? It's a perfect factor. It's a factor that goes into it. So if I was to divide this original equation by this equation that we just got, it would give us a nice, even, whole polynomial without any remainder in the end. That's the point. Do I have any questions about that?
When we do questions like that, will it basically just be trial and error?
It's a good question. It is trial and error, with keeping in mind that it has to be, there we go, a factor of negative 24. Yeah. I was going to go through remainder theorem today, so rational root theorem. It's the complicated version of this, so what I might do is I might just leave it for next time. But there's one last thing I want to mention, and the last thing I want to mention is just these two formulas here. In general, P of x equals to x cubed minus a cubed. What is that very similar to? What is that formula very similar to? Does it remind you of anything, Keely? Look at the name. Difference of cubes. And it's relevant because we did difference of. There you go. It's very similar to the difference of squares formula. All you need to know is that this formula exists and this formula exists because they work. I'm not going to delve into too much, but the idea is that if you see something in that form, or you can make it into that form, just factorize it using that. I'm not going to go through the rational root theorem today. I'm going to set that as, you know what, I'll say, during the holidays, I want you to make sure you understand what I've gone through very thoroughly. In the textbook, it's listed as where are we up to? Oh, I'm on the wrong exercise. It makes sense I couldn't find an example. The factor theorem, and we went through something called the remainder theorem as well. On page 224, it goes through an idea called the rational root theorem. It is an extension of what we just covered today. particularly where I said that the first term has to be a multiple of the two first terms in our factors, and the last terms have to be factors of our constant. What I want you to do is, over the holidays, I want you to obviously make sure you understand everything I covered today with the factor and the remainder theorem. And then once you've done that, I want you to read through page 224 and 225 and try your best to understand the rational root theorem. When we come back, I'll recover the rational root theorem because it is a more difficult concept. But right now, I want you guys to focus on understanding that factor and the remainder theorem. It's a very difficult concept. Do you have any questions? Okay.